time we are doing the, the exponential equation. Exponential equation is equations. We're doing 3 examples, but today we are doing more. I did the first 3 examples is straightforward. But now it's easy, but no a little bit tricky, picky, sophisticated. However, they are another very, very complicated. So exponential equation is equation, but the unknown or the variable is located in the exponent part. So you need to apply a specific procedure in order to eliminate the exponential part, and you somehow magically you convert to linear equation or quadratic equation without exponent. And the key idea that we studied so far is using the common base. You will be able to express both sides of the equation using the common base. Nice. Nice. Let's see example 4 is square root 3 raised to the x plus 4. X plus 4 equal 3 to the x. Okay, I introduce one, new thing is square root. But you need to know, that square root 3 is equivalent to say 3 to the 1/2, no? You remember, I suppose you remember the idea for the fraction exponent. Entonces es obvio que the common base we select in this problem is 3. Because 3, radical 3, we can express it like a 3 to the 1/2, and 3 is 3. So 3 is 3 to the 1/4. If you manipulate both sides, you copy 3 raised to the 1/2 raised to the x plus 4 equal 3 raised to the x power. And this is very, very common in this problem, because you have different level of the exponent. And you know the rule of the exponent, que you multiply the exponent, ¿no? Entonces 1/2 is 3 1/2 times x plus 4. Don't forget the parenthesis, because 1/2 multiply everything in the expression, because by the way, it's a binomial, equal 3 to the x. Now we are ready. So you have 2 exponential. And if the base is the same, it's because the conclusion. Okay, let me write in this language. This is I don't like the student cancel out the base. Actually, yes, practically yes, it's a shortcut. However, it's not theoretical right. Okay, because the thing we are doing this is because the function is 1 to 1. Therefore, so you have same value of the function, we have same value of the x value. So then the conclusion is you copy 1/2 parenthesis x plus 4 equal x. Wow, and magically the 3 disappear. Cool. Now, solution of this linear equation is too easy. Suppose that I don't feel comfortable with the fraction. Okay, no problema. You multiply by 2 both sides of the equation. So 1/2 times 2 is 1. So it's x plus 4 equal to x. Entonces 4 is equal to x minus x. 4 is equal to x. And it's the answer. X equal 4. Not necessary checking in this equation. And the reason it's not necessary checking is because the exponential function domain is all real numbers. You are doing well. In algebra, you can checking any equation that you find solution. But some special equation that we studied before, radical equation, is mandatory checking, because during the process of the solution, you are doing some transformation Therefore, in one step, you are working with the equation that is not 100% equivalent to the original. In this case, yes, always happen, no problema, because exponential is nice function because domain is all real number. Do you follow me? Yes or no? Okay, Johan. Joshua Gomez. Joshua say okay. Okay, one more example. Oh, this is easy, and you help me. 2 raised to the 1 minus 2x. This is 1 minus 2x expression is exponent. Some students say 2 parentheses 1 minus 2x. This is wrong. No, this is exponent. This is small. Equal. In the right hand side, we have 8 raised to the x plus 1. And what, in your opinion, what is the common base in this example? Common base. 2, obviously, because 2 is 2. And a is 2 to the third power. Very well. Now we have 2 raised to the 1 minus 2x equal 2 to the third power, which is equivalent to 8 raised to the x plus 1. Now one more time, rule of the exponent, multiplication. 2, 1 minus 2x equal 2 times 3 multiply x plus 1. Very important, this parenthesis, because 3 multiply whole thing. And to indicate this idea, you put the parenthesis. Now, again, ready to exponential with the same base, then the exponent is the same. So 1 minus 2x is equal to 3 times x plus 1. Linear equation, super easy, classical idea. Apply distributive property, combine letter, and solve for x. Multiply here. You have 1 minus 2x is equal to 3x plus 3. In order to isolate the x, there are many ways. However, I prefer take the positive guy, get 3x, move it minus 2 to the other side like a plus 2. This one stay here, minus 3. Okay, this is negative 2. And this is 5x. Finally, divided by 5, both sides. X alone is negative 2/5. And exponent, or the variable and the exponent maybe are all real number domain. So it may be positive, maybe negative, maybe 0. No restriction, no problem. This example 5 is clear? Yes or no?
Yes.
It's important that you, any question you have, don't be shy. Okay, I enjoy explain. Okay, but I want smart questions. For example, a stupid question is, I don't understand anything. Because you don't give me any clue to explain, no? Professor, in the last part, in the last line, or not necessarily you say the number, no? In the part you eliminate the exponent. Why? So you give me a clue to say I understand. Okay, this is a little bit confusing, but we are using our imagination. Suppose this, 2/3 fraction. I don't like fraction. Raised to the x power is equal 9/4. Wow, what the hell? What do you think? There are connection, there are relationship between this number or no? Forget about the fraction. Let's analyze independent, one by one. For example, 9. 9 is connecting somehow with the 3, yes or no? Because it's 3 to the second power. Okay, because I try to connect in right hand side, left hand side, but the problem is, bueno, professor, but 9 is in the top and 3 is in the bottom. No, it's not important. Not important because remember we're using negative exponent, and negative exponent finds reciprocal, flip it that. And likewise for let's do the second power. Okay, now this is equivalent to say 3 squared divided by 2 squared. And the same exponent is 2. This is 3/2 squared. Do you follow me so far? So I try to do my best, no? I try to manipulate both sides in order to express it in the same base. But in this moment, is the same base or no? What do you think? No? Yes? No? Yes? No? Something is weird, huh? Opinion. It's easy. The solution is easy, eh? Come on. You see again the left-hand side. Left-hand side, the base is 2/3. In the right-hand side, now, in this transformation we are doing, is 3/2. It's not the same, of course, it's different, but they are connection que es reciprocal. Yes or no? Entonces, si you flip it, one of these, doesn't matter. What do you prefer? You put a negative exponent. So I can write that like that. 2/3 raised to the x. I make a decision, I don't know why, to switching the right hand side. I put 2/3, o sea, reciprocal, but the exponent is -2. Do you see the transformation? Cool or no?
Yes, cool.
Okay. If we have two exponential and the base is the same, it's because the exponent is the same. Okay. It's obvious que es -2. Final answer. So you need to be aware for any possibility. Radical, exponent, que es exponent fraction, reciprocal, que es exponent negative. One easy. Suppose 32 raised to the x plus 2. I need help in this. Equal 16 raised to the 2 minus x. Again, the same challenge. What's the common base? In this problem, what do you think? It's 4. No, I don't think so, because 4, okay. 4 is Jenny say que es 4. Let me try to analyze the Jenny proposal. Is 4, 16 is 2, Gladys. Okay. 4 no, Jenny, because 16 is 4 to the second power, but 32 no. 32 we cannot express it like exponent 4, because 4 to the 1 is 4, 4 to the second is 16, and 4 to the third is 64, y 32. Oh, okay. Entonces es obvio que es 2. Es obvio que es 2, the common base. Okay, entonces let's try. And the common base was 2. You can express it 16 like a 2 to the 4 power. Wow, using the common base too. And 32 is 2 to the 5th power because 2 times 2 times 2 times 2 times 2, 5 times is 32. Okay, I discovered the common base. Now replace. No, the original number, no. 2 to the 5th power raised to the x plus 2 is equal to 2 to the 4th power raised to the 2 minus x. One more time, we are doing the multiplication of the exponent, to say 2, 5 parenthesis, x plus 2 equal to 4 parenthesis, 2 minus x. Again, see we have two exponential functions and the base is the same and they are equal each other, of course. That's because the only possibility is that the exponent is the same. 5x plus 2 equal 4, 2 minus x. Magically, using this procedure, you convert the exponential equation in linear equation or quadratic equation, depende, no? Depende the example. The most common is linear. So you apply this derivative property, 5x plus 10 equal 8 minus 4x. Okay, ready. 5x stay here, plus 4x here is equal 8 minus 10. This is 9, and this is minus 2. Divided by 9 both sides. X is equal minus 2 over 9. Boom, final answer. Super cool. Yeah, that's the answer. I have my piece of paper. Okay, one more, and I want to explain new concept. We are doing two more using the new concept. Okay, one more classical example 8 is cubic root of 5 raised to the minus x. Wow, complicated because we have cubic root, we have negative exponent, boy, and we have 1 over 5, 1/5 raised to the x plus 2. But I know very well that I can express it cubic root of 5 using the base 5, no? And 1/5 I can using also base 5, no? Using negative exponent because it's a reciprocal. So in conclusion, you copy in one corner of the piece of paper, something like that. Cubic root of 5 is equal 5 raised to the 1/3 using fraction exponent notation. And 1/5 is 5 to the negative 1. Because I know very well, when you raise to the negative 1, in general, negative exponent is reciprocal. But negative 1 is perfect reciprocal because it's 1 over 5 to the 1, no? That this 1 go to the bottom, positive. So you replace. It's a 5 raised to the 1/3 raised to the minus x, double level of the exponent. And here we have 5, negative 1, x plus 2. So basically, the common base that I am using this example is 5. F5. And this example. One more time, we are doing the rule of the exponent. You multiply. You multiply, you have minus 1/3 x. This. Right, so the base stay, you multiply this and this. And the other side is 5 minus 1, que es invisible, x plus 2. Again, we have two exponential functions, same base, is because then, either way, using the language of the if-then, is the conditional. Negative 1/3 x equal negative x plus 2. Double negative. you multiply by negative or multiply the entire equation by -1 if you want to put a positive, but I prefer eliminate the fraction. Because the multiplication, the entire equation by -3. So this is negative positive, 1/3 times 3 is 1, this is just x positive. And this is negative positive again, 3x plus 2. Wow, nice equation, no fraction anymore, no negative anymore, because I don't like. You apply distributive property is 3x plus 6. Now finally, x minus 3x equals 6. X minus 3x is minus 2x equals 6 divided by -2 both sides. X is equal minus 3. Minus. Okay, let me see. Yeah, it is. I check it in my piece of paper. Okay. No problema. Okay, so now, after that, I have two more examples of the exponential, but this exponential, this example of the exponential contain one special number, que es the number e, que es the number e. The number e is a famous mathematical constant that we are using in this part of the exponential and logarithmic function. And this is the irrational number, I want to prove in detail the irrational number. First of all, the definition of the E, que is the Euler constant, Euler number, is irrational number, irrational because contain infinity decimal place. The definition is is a limited when the x approaches to infinity of 1 plus 1 over x raised to the x power. You don't know very well the idea for the limit, but it's easy to understand because basically the only thing you should do is plugging in, so replace the x for the big number. Infinity means huge number. And to do this, I create for you one Excel spreadsheet. Illustrate very, very well this idea. Let me show you. Let me share the screen. Okay, there you go. Excel. Do you see the Excel?
Yes.
I put the number here. 1, 2, 3, 4, 5, 6, 7. I increasing to 1,000. And here I put the formula of the Euler. Is 1 plus 1 over the number inside the parenthesis raised to the n power. This is definition. When you see a mathematical guy, this column and equal sign indicate definition. This is one formal, symbolic, mathematical indicate definition. Okay, now I'm increasing. Wow, look at that, too much. 100, 200, 300. Wow, let me go fast. And one moment I am boring to 1,000 something, but I can continue if you want. This is super easy. The only thing you should do is copy here, drop, and you see it look like a 71, no? 71, 2.71, 6 something. I do the graph to understand this visually, I do the graph. Because here it's hard to see. However, I do the graph. And the graph look like that. And the x-axis, I put a number, 1, 2, 3, 4, 5, 1, 2,000 something. And the y-axis is important, the answer of the formula. It's 2 point something, 2.5, 2 point, in between 2.5 and 3, in the middle maybe it's 2.75, but this 2 point not exactly 75, 71. This is the constant. I take this picture in internet and Google image for the number e que have infinity decimal. Of course, you don't need to memorize this. You take in any calculator, you put e, and automatically you see the decimal approximation can have our specific calculator, que not necessarily is the same for any calculator, no? So you put it here e to the 1 power, no? The answer in decimal is, in my calculator I put now 2.71828. Okay. Exactly this approximation, the first line in my calculator. And so what is important is, it's important because when you study now in a few minutes the logarithmic functions, we can, in one moment, we can make a decision on a standard base using. So what in this case, the exponential, we're using base 2, base 3, base 5, base whatever. But this base is special because when we study the logarithmic function, it somehow is connecting with the exponential. Let's see how. You see that this logarithmic, the base is e, is the name, the official name is natural logarithm. I want to repeat again in your moment. But these have super important property in calculus. Okay? In calculus. Okay, I suppose that everyone need to take calculus, right? Okay, in calculus, this is super important, this number. E. Okay, so now let's do in one couple of the examples so you understand a little bit, not too much, the definition of E. It's irrational number. We cannot represent like a fraction. So you represent like a decimal, have infinity decimal places. Okay, now we are ready to use it a little bit. Not too complicated, but a little bit. Suppose one couple of problems can involve somehow E. Example 9 and example 10. Okay, example 9 is E 3 minus x equal E to the third power raised to the minus x. This is example 9. Example 10 is E to the x minus 1 equal parentheses 1 over E to the fourth power raised to the x plus 1. In any case, my goal is solve for x. Okay. Entonces es obvio que en both scenarios, the common base is E. And so far, you need to understand that E is using to a standard base. So any exponential, I promise that I want to explain it in your moment, not now. Any exponential using base 2, base 3, base 4, we can standardize using the common base E. Okay? Okay? So now I apply the rule of the exponent. This stays the same. I don't touch. However, this, yes, multiplication of the exponent is e to the minus 3x. One more time, we have two exponential, by the way, standard. If the exponent is the same, exponential is the same, and the base is the same, so the conclusion is the exponent is the same. 3 minus x is equal minus 3x. Okay, I try to do my best in linear equation. Minus 3x plus x. While I term is minus 2x divided by negative 2 both sides. The answer is x equal minus 3 half. Okay. And number 10, similar, but the only thing I see is reciprocal here, reciprocal, but I fixed the reciprocal. How? Using negative exponent. So this is equivalent to 1 over e to the 4 power. In my mind, is equivalent to say e to the minus 4 exponent. So e to the minus 4 raised to the x plus 1. Okay, one more time, you apply the rule of the exponent, different level, multiplication, e to the minus 4 times x plus 1. Okay, again, if we have two exponential and the base is the same, then the exponent is the same. X minus 1 equal minus 4 x plus 1. Linear equation, super easy, no problem with us. Apply distribute the property here. X minus 1 is equal minus 4x minus 4. Okay, now ready. Well, I propose you, for example, this x stay here, bring down, plus 4x, I move to the left. In the right hand side, I have negative 4 plus 1. This is 5, and this is negative 3. Divided by 5 both sides. Yeah, x is equal minus 3 over 5. Okay, so we are doing a quick tours for the exponential equation using this elementary straightforward idea. You have to express both sides using the common base and magically disappear the fraction. Okay, now I propose you one idea. Okay, I explained the last class, but I repeat again. There are equations, these are the most popular equation, exponential equation. It's impossible to do it in this way. For example, straightforward example, but impossible doing this way. Suppose 2 to the x power equal 3. Okay, impossible. Impossible express a 3 using base 2 or base 2 using base 3. Si es 4, yes. Si es 8, yes. Because it's power of 2. Or si es, here is 9 or 27. Because it's power of 3. But in this case, it's impossible using this way. And so we have solution. Of course, we have solution, but the solution is to find a solution. We need to study a new idea. So I propose you. This equation is the first equation that we're solving when you understand this new idea. This new idea is a logarithmic function. We study logarithmic functions. Pay attention. Okay, here, always the students say, no, I don't understand the logarithmic function. It's easy. Logarithmic function. What is the definition of the logarithmic function? Well, the logarithmic function is the inverse function of the exponential. That we have, for example, the logarithmic function, to the base a where a is always positive number and never 1 or 0. This is illegal. Illegal. This is trivial. And negative, does this sound familiar? Because you know very well the restriction for the base and the exponential equation. So basically, entonces, what is the definition? The definition is the logarithmic function is surprise, is the inverse function of exponential. Of course, of the one exponential que somehow is connecting with the same base. No arbitrary, crazy. No. O sea, the idea is clear. Let me explain in detail now. Suppose you are super familiar with exponential function. Okay, everyone know very well exponential function is f of x equal 1 base raised to the x power. And the base, remember, always positive, no 1, no 0. This is the classical exponential function. Now, what is the logarithmic function, professor? It's inverse. Now, inverse, remember, you replace f of x for y, okay, and you interchange x and y. Okay, to say is x equal a to the y, something like that. And this is the inverse. This is the inverse. But the problem is the inverse is an implicit. Implicit, no good, no clear, implicit form. I need professor and explicit. I need the inverse and explicit. Explicit form. And explicit is when the y somehow is isolated. But to isolate it, we are using this notation, new notation. Y alone is equal, and you put a name of the function, that is log, logarithmic function. You put a small number here, a small number that represent the base and in the argument of the function, because basically this is like a function notation, f of x, no? But the problem is the name of the function is log. A specification, the base, que by the way is the same base que come from for the hypothetical exponential initial function. And the argument, you put this. Okay? It's a definition, but I don't understand very well. I need to see more clear interpretation, example to understand this. Let me try to do my best. So the only thing que I would like you know so far is que the logarithmic function, que is the new function that we study, because we are studying because this function opened the door to solving this equation, exponential equation that we never can solve it using the traditional common base method. Now this opened the door, but this guy can open the door is the inverse function for the one exponential associated with the same base. But what is the interpretation? Si es the inverse, I know que interchange, range, and domain. For example, interpretation. To understand this, I propose you split the page in two parts. And here you put exponential. Exponential statement. Way. And here we have now logarithmic. Statement. And we write any exponential here, we somehow convert to logarithmic, because you can express one statement in either way, in exponential or in logarithmic. Let me explain. Suppose elementary, can I get it? 2 to the 5th power. is equal to 32. Because I know, okay, when you multiply 2 5 times, 2 times 2 times 2 times 2 times 2 is 32. How you translate this statement in another way is logarithmic statement? Well, you put the famous word log, okay? Your specification using a small number here at the base. The base is 2. How do you know it's 2? Because it's the base for the associated exponential. Inside the parentheses, you put the number, and outside, give me one number. Inside the parentheses, 32, and outside the parentheses, 5. Wow, entonces I need to understand. Logarithmic function, give me what exponent, the answer of the logarithm is the exponent, what exponent is necessary to raise to, get the base, in order to get the number inside the parentheses, the argument is 32. Okay? Another example. Suppose 3 to the 4th power. Do you follow me or no? Keep in mind, keep in mind, keep in mind, the answer que offer the logarithmic function is exponent. And your specification, the base, and your specification, the value that you want to obtain according to the exponential, no? For example, this 3 to the 4th power is equal to 81. It's logical because I know that 81 is 9 times 9. 9 times 9, 9 times 9. And 9 is 3 and 3. Yeah? 3 and 3. Actually, we have 4, 3. 1, 2, 3, 4 multiplication, give me 81. And the word of the logarithm, you put log. It's obvious that the base is 3. Parenthesis equal. I know very well that the answer is 4 because the answer of the logarithm is always the exponent. And of course, the number inside the parenthesis is 81. Cool? In general, see, I want to memorize this. In general, you have base. Look at that. Base. Okay. You have base. You have here in the exponential statement, you have, okay, let me try here. You have base, base, and this example was 2 and 3, no? In general base, I call, raise to the 1 exponent, 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 and this give me a number I want to call result. Okay, this is in the name I put it to understand in the exponential. And the logarithm, when you switch into logarithmic, by the way, I put double arrow because you can convert from exponential to logarithm or from logarithm to exponential. It's very, very popular because somebody don't understand very well logarithm. They say, no, I don't understand. But I switch into exponential. Yes, you can. And you switch into exponential. Oh, I understand now. So you copy the magic word log, your specification using a small number, the base. In this example was 2 and 3. And the answer get offered is exponent. Okay. And the number that we have inside the result is the result of the hypothetical exponential. After I promise we are doing conversion in both directions, but before that, I want to discussing. Okay, but the idea today is intuitive idea for the logarithmic. Next time, guys, it's important. Everyone needs scientific calculator. Scientific calculator. Scientific calculator, no too expensive. No, cheaper. But I recommend, for example, let me try. I recommend, I have the image of this. I recommend, let me see. This. There you go. This calculator is easy. Or another version of this calculator. Let me try to see. I have another image here. This is the only one I have. This calculator is easy. You can buy and Walmart, this depot, even in the library of the our campus, the bookstore, so the our campus. Very scientific. It's important because we are using the special function log. Look at that, log. Logarithmic function is located here. We have two logarithms, log, and we have lm. I want to explain in a few seconds. Okay. So this is impossible doing without calculator because we are working with a special function. Okay, so we need calculator to pass this test. Okay. Okay. Now let's practice intuition. No calculator. No calculator. No. Just intuition. Today, no calculator. Today, intuition. To understand much better, I propose you logarithm base 10. Because logarithm base 10 is super easy to understand. Logarithm base 10 of 100. Let's compute this without a calculator. Okay, entonces, professor, I am totally lost. Somebody know the answer? Or no? So I put example. Logarithm base 10 is super easy to understand. I don't know. Maybe 2, maybe 4, but 10 is easy. 10 is easy. After I put another example, but I want to discuss on 10. Question mark, you don't know this. Somebody have idea what is the value without calculator? No? No? Come on. No? Yes or no? You answer yes or no. Come on, guy. Are you here or you are sleeping? No idea? Answer me. No? Yes. 2. Gladys say 2. Gladys says 2, professor. Okay. Gladys, you put in the calculator or no?
No, I just kind of did it from my head.
Okay, cool. Let me explain, guys, the systematic way to do this. You have no idea. You put X. When you don't know something in algebra, you put X. So I recommend you convert in this direction to exponential. You put it here in the test. Put the arrow and you put exponential. Conversion to exponential. Everyone understand the action we are doing. So it's similar to this picture. Okay. But in this case, we are doing in this direction, no? From logarithmic to exponential. Because I am confusing. I don't understand very well the logarithm, but the exponential is more clear for me. Entonces, you copy the base. What is the base? The base is 10. The exponent, no idea. And the answer is 100. Okay, this statement is equivalent 100% with this. This is a logarithmic statement and this is exponential statement. But I know very well that 100 is 10 squared, is 10 times 10. Therefore, we have 2 exponential and the base is the same as 10, therefore the exponent is the same and the answer is x equal to. Boom. without calculator. Of course, the majority of the example is impossible doing this way because normally the majority of the logarithms are irrational numbers. Okay. Okay. Now, what about logarithm? We continue logarithm base 10, and you help me. 1,000. Using this rule, using this idea, what do you think? No? Nobody? Gladys, only Gladys, no? Gladys es 3, Gladys, no, pero Gladys, no, Gladys no. Gladys, stay quiet. Es 3. Bueno, entonces, according to the rule of Gladys, it's super easy because the only thing you should do is count how many zero? 1, 2, es 2. And 1, 2, 3 es 3. Wow, it's easy the logarithm. Bueno, it's easy in this scenario que es base 10. And 1 million, what do you think about 1 million? It's 6. Okay. But I want to complicate your life now. Using exactly the same idea. But I want to complicate like that. Logarithm base 10 of 10. Mm. Mm. You can use intuition, but if intuition fail, it's not clear. Es one, intuition one, it's obvious, no? Suppose que the intuition is fail. The answer is one, she's right. Logarithm 10 is 10 is 1. If you convert to exponential, the base is 10, the exponent, I don't know, is equal to 10. But 10 alone is 10 to the 1, therefore x is 1. Super clear, right? And this idea is applied not always in 10. It's applied in any number. For example, logarithm base 2 of 2 is 1. Because the exponent can necessarily raise the base 2 in order to get the same value as 1. Logarithm base 3 of 3 is 1. This is super important property. Logarithm base, any base of the same number is 1. Keep in mind this. Okay. Okay. And what about logarithm base 10 of 1? Wow, this is very, very weird. Very, very weird. No idea? Nobody? Nobody? No, that? No. See, the intuition failed, no problem. I try to do by the systematic way. What is the systematic? Es zero, es zero, es zero. Es zero. Es zero. Okay. Then. Claro, it's zero. Claro, it's zero. Suppose I don't know. I put an X here. I convert to exponential. This arrow indicates us conversion to exponential. The reason is 10 to the exponent I don't know is equal 1. But you need to know que any base raised to the 0 power is 1. Not only 10, any number raised to the 0 power or expression, therefore x is 0. Keep in mind another important property. In your moment, I want to summarize again. Logarithm of the any base of 1 is equal to 0. Wow, amazing. The student can take this class and need to know by memory property 1 and property 2. Okay? But I want to complicate a little bit more. Okay, look, what is the logarithm base 10 again? I am using logarithm easy, que es base 10, to understand intuition of the point 1. And this is without calculator. In the other class, we are checking with the calculator. Pero basic today is the idea of the interpretation logarithmic functions. Okay? Interpretation. No idea? Nobody? -1. Very, very well. -1. She said that the answer is -1. Let me prove. Let me prove. Let me prove. Don't worry. Be happy. You don't know. You put X. Immediately, I don't understand. You convert to exponential. Yes. You convert to exponential. And the exponential is the base is 10. Look at that. This 10 is a small 10. I put a big 10 in the exponential. The exponent is X. And it's a 0.1. And 0.1 in fraction is 1 over 10. And 1 over 10 is reciprocal, is 10 to the minus 1. Therefore, we have two exponential, same base, therefore X is -1. Cool? So you can do always in this way. One more for a moment, and that's it. Suppose 0.01. What is the answer of this? Using similar idea. No clear? Gladys, Gladys, no. No, Gladys, no. Es negative. Okay, es negative, es negative. Let me prove. This is, you put X because you don't know, you convert to exponential statement, the base is 10, the exponent I don't know, and this is 0.01, and 0.01 is equivalent to say 1 over 100, reciprocal 100, and 100 is 10 to the second power, and reciprocal is 10 to the -2, therefore, same exponential, same base, X equal -2. Clear? Let's do some problem, intuitive problem, in which you compute without calculator, no calculator, no calculator. Everyone follow me, guys? Do you understand? A little bit, not too much, but a little bit logarithmic function.
Yeah.
See, one friend say, what thing you study right now in mathematics? No, I study logarithmic function. What the hell is logarithmic function? How you define that? What is the logarithmic function? In your own word, in your own word, no sophisticated. Huh? No idea? Es the value of this point. Yeah, it's the value of this point. Yeah, it's the value of this point. It's the value. Okay, okay. Okay, let's do in this problem. Compute that without calculator. Number one, logarithm base 4 of 64. Boom, question mark, without calculator. Of course, in your moment, I want to explain how we compute this using the calculator. No? But now, today is without calculator, or at least the first part of today. Okay, intuition. Gladys is 3. Okay, Gladys 3. Always Gladys, right? However, I want to suppose that I don't know. You have no justification to understand. No, you put X, you convert to exponential because I don't understand very, very well the logarithm. However, when I convert to exponential, the door is open. Wow, yeah, I got it. I understand now. Because I asked by myself 2 questions. Question 1, what's the base? What is the base of this logarithmic function? What is the base? 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 The base is 4, Jenny. So this 4 that you see small here, you put big one. That's the base en exponential. Okay, entonces now the number 2 is what is exponent? What is the exponent? in this exponential statement. What is the exponent? What is the exponent? What is the exponent here? The exponent is 64 or is x? Es x. The exponent I know is x because in the logarithmic give me the exponent que es necesario to raise 4 in order to get 64. Equals 64. Wow, amazing. In this moment, Edward. In this moment, Edward, you have in your face, in front of you, one elementary exponential equation. Okay, you realize that 64 is 4 to the third power because 4 times 4 times 4, 3 times is 64. Now you have two exponential, same base, therefore x equals 3. Boom, final answer. Okay? No necessary thinking. No. Es, you see the logarithm statement, you convert. Sometimes it's backward. Sometimes it's better. The majority of the scenario is like that. You have logarithm statement, you don't understand very well. You change to exponential. Oh, I see the answer. Sometimes no. Sometimes it's backward. Sometimes it's exponential and it's not clear. And when you apply logarithm, it's more clear. Let's do a number 2 example. Compute logarithm. I did before. Compute logarithm base 10 of the 1000. Do you remember this example? I did before? Yeah. Clara dice yes. What's the value? The value is, I don't see. 1, 3. 3. Jenny. 3. Do you want to do again or no? No. 3. Okay. You want to do again? No. Number 3. Oh. Look at that. Thinking this is very, very, no hard, but confusing. It's a little bit counterintuitive idea. Suppose logarithm base 5 of the 1 over 125. Without calculator. Es negative 3. Yes. She said que es negative 3. Okay, intuition. Suppose intuition. Let's do it in the systematic way, but intuition is the connection between 125 and 5 is 5 cubic. Yes or no? Entonces sound familiar, ¿no? But this is reciprocal. This is reciprocal is negative. Exponent. Okay. No, I don't understand that. Let's do it in the systematic way. Systematic way, you put an x here, equal to exponential. The convention is, guys, when you see one arrow and you put 2 exponential, is that you are doing this conversion from a statement, logarithm statement to exponential statement. And the base, remember the 2 important questions. Question number 1, what's the base? 5. You put the big 5. No small, big. What is the exponent? The exponent is exactly I am looking for. It's equal 1 over 125. Oh, more clear now. This is classical mathematics. Maybe mentally it's hard. However, when you write the piece of paper, you see more clear. Because the majority of the information is coming from the eyes. Now, 125 is 5 to the cubic power. Look, I replace. No 125 anymore. It's 5 cubic. Using this idea. Now reciprocal, is 5 to the minus 3. Reciprocal. Therefore, we have 2 exponential and the same base. Therefore, x is minus 3. Cool, right? Entonces, my recommendation is doing that way, no? Because sometimes mentally it's no Not clear? Okay. Now, number 4 is the last example. This is tricky, super tricky. Logarithm base 1/2. Professor, I never see in my life the base 1/2. Remember definition? Definition of the base. Base is a real number, no negative, no 1, no 0. But otherwise, yes, it's possible. So the base maybe is a fraction, pero positive. Or no, or so one possibility of the base is 2.5. Why not? Decimal base, radical 2, irrational, crazy. Okay, entonces now I have no idea, no? I have no idea. I put x. Now you convert to exponential to understand more clear. Remember 2 questions. What's the base? Oh, the base is 1/2, professor. You put big 1/2. The exponent is the thing I don't know. And the answer is 4. And this is my new exponential equation, que es easy, using common base. Base, suppose que es 2, es negative 2, yes, you're right. The common base is 2. Entonces, you're right. This is reciprocal. 1/2 is 2 to the negative 1, raised to the x, and 4 is 2 to the second power. Okay, now the rest is multiplication. Different level of the exponent is 2 to the minus x, because negative 1 times x is negative x equal to the x to the second power. You have 2 exponential, and the base is the same. It's because the exponent is the same. So the conclusion is minus x is equal to, but I don't want minus x. I want x alone as negative 2. Cool? Cool? Okay. Okay. So now I am ready, or at least I believe que you understand definition of the logarithmic function. Okay? You know que logarithm is the inverse function of the exponential. Now let's study now formally the property of the logarithmic function. Let's study now formally. This is the intuitive idea. You get the intuitive idea. The intuition is okay. Let me try formally. And what is the formally? It's the property, domain, range, x in a set, y in a set, asymptote, something, no? Common, typical common points. Entonces now, let's study now property of logarithmic function. We study now the basic property. I propose you, I don't know si today or no, another complementary property. But the basis, for example, domain. Number 1, domain range. Bueno, professor, you say que the logarithmic function is the inverse function of the exponential. And we studied domain and range of the exponential last class. Let me recall. Domain of exponential is ordinary number. When you say in the problem that we are doing in the exponential equation, the exponential equation is nice because I said ordinary number. This is the reason. However, the range, no. Why no? Well, the reason is because I suppose you remember a little bit the graph of the exponential function. They look like that, right? Passing through the famous point 0,1, it's asymptotically to the, so we have here horizontal asymptote at y0 You never see exponential in the negative part. No, illegal. So the answer offer any exponential doesn't matter, regardless the base, 3, whatever, is positive. Entonces es 0, infinity. Es the range. No include 0 because it's asymptotically I never touch. This is the thing we studied last class. And you apply this idea in the new class today, que es, si es de inverse, interchange domain and range. The domain of the logarithm is the range of the associate exponential, and the range is all real. Okay, so now I want to stop a little bit to understand much better this. You say, Professor, que only logarithmic you can apply in positive number. Okay, so logarithm base 10 of 100 is 2. But logarithm base 10 of negative 100 is completely out the domain. Look, it says to be undefined. Logarithm of the negative number is impossible. And what about 0, Professor? 0 is not included inside the domain. It's also undefined. Be careful. And after, when you're using the calculator, by curiosity, you put logarithm of negative number, automatically you see error. And logarithm of 0, you see error out the domain. Okay? Okay, logarithm of the positive number. No 0, no negative. Okay. This is the property number 1. The property number 2 of the logarithmic function is the famous x in a set que we are using in any function that we studied before, and y in a set. Well, the x in a set. Well, I know. Let me compare with exponential again. And the exponential we study here, que the y in a set, sorry, is the famous point 0, 1, que es universal. I call universal point. Okay. And the x in a set do not exist. Do not exist. Because the exponential never cross or touch the x-axis asymptotically. So this idea is similar to the logarithmic because it's reciprocal. The only thing you are doing is interchange x and y. It's obvious, you see in the last class of the inverse function, the y set in one function, the value interchange x and y corresponded with the x in a set. So the x in a set and the logarithm is 1, 0. Oh, I'm making sense because the professor just explained the logarithm of 1 is 0 of the any base, because any base raised to the 0 power is 1. Therefore, 1, 0. And the y in a set do not exist. So it's like you interchange this and this information. But keep in mind that you interchange x and y because we are talking about inverse function. Make sense? Okay, this is the property. What is the property number 2? I am confused, Professor. Well, the property number 2 is x in a set and y in a set. Okay, cool. However, we have similar situation of the exponential. We have, for example, a logarithmic of the any base of the number, but you have two possibilities. You have the possibility that the base a is bigger than 1. See, a base is bigger than 1, the function is increasing. Very, very similar to exponential. And if the base is positive, but in between 0 and 1 is decreasing. I want to take advantage this moment to explain one idea. Look. In one example we are doing before, so suppose we have logarithm of 1/2, base 1/2, sorry, of 4 is equal -2. Okay. In this scenario, it's not the most popular, but it happen. The base is in between 0 and 1. That is an area. However, the number here, no, is greater than 1. The answer is completely negative. And the idea behind this is that you need to find reciprocal something. Okay, likewise, another example that we are doing before, logarithm base 5 of 1 over 125 is -3. Why -3? So when the number here is greater than 1, but the number here is less than 1, they are contradiction. So now you need the negative exponent to make it a reciprocal. Okay. So we have two families of the logarithms. Similar, we have two families of the exponential. Remember decay and growth. We have two families of the logarithm, but no, now I want to do the graph after that. Okay, number 4 property is the typical point. Typical points. Remember, to make roughly graph by hand of the exponential or the logarithm, we need only 3 points. 3 points and the asymptote. Okay, so the typical point are 1,0, que is the universal. This is the universal for logarithmic function. The function. The universal for exponential is 0,1, but the logarithm is 1,0. Okay. Another is the base, 1, because I know the logarithm of the base a of a is 1. So this idea is logarithm base a of 1 is 0. Okay, this is 1 point typical, 2 point typical, and another typical is 1 over a, comma -1, que is the reciprocal, because logarithm base a of reciprocal is equal -1. This idea is clear? Because the reciprocal and reciprocal somehow involve negative exponent. Let me prove this part. Suppose that I don't know the -1. You put x and you convert to exponential. The base is a. I copy big A. This small a, I copy. The exponent, I have no idea. Equal 1 over a. And this is a to the -1. Therefore, to exponential, same base, x is equal to -1. And this is the typical. And this is the typical point. Suppose in the test, for sure the test include a graphic of the logarithmic and exponential. Suppose I want to do the graph of the logarithm base 2 of x function. Entonces, one easy, short, fast way to do that is, look at that. You have the plane, x and y. You plot 3 points, que the point is a universal point, que is here, 1,0. I plot this point. Plot that. Boom. The second point is this, que in our specific example is 2,1, because the base is 2, no? 2,1 is, this is 2, and this is 1. I plot the second point. This point is the point, 2,1. And we continue if you want, pero always power of 2. So 2, 4, 8, 16. Suppose que 4, 3, 4 es 2, no? That's all. What about between 0 and 1? Because we have domain here. Suppose this point, because I did a point, sorry. And now this point gets 1/2. 1/2, comma, -1. I plot this point. 1/2 is here. And between 0 and 1. Here, 1/2 in x-axis. And the y-axis is -1. And -1 is here. -1. So I plot that point. This is this. Oh. If you connect it somehow, and you connecting more points, I want to show you in this one now. You see something like that. And this is the graph of the logarithm base 2 of x. Okay, que es completely symmetric. Remember the idea behind the inverse function, the famous line, que es the line que represents the identity function y equal x. Here, right? Okay, now. See, you, for example, you are using another color. The exponential associated with this is super easy, because the only thing you should do is interchange x and y. So at this point I forgot, is 1/2, comma, -1. Entonces this point and the exponential would be -1, comma, half. So it's -1 is here, I suppose. -1, half is approximately here, right? This point is, look, -1, comma, half. The only thing I did was interchange x and y to obtain another function, because it's the inverse function. And the famous 0,1 universal for the exponential is the is flip that, interchange this. And another point is 1,2. 1,2 is 1 and 2 here. This point is the point, 1,2. Let me try to connecting the exponential, look like that. It's obvious in this case it's exponential growth because the base is 2. Entonces es increasing. This is the function 2 to the x, exponential. And this is the function logarithm base 2, que es the inverse of this. And you see the symmetry. Oh, one more thing, important, 3 important. I know very well that we have horizontal asymptote here for the exponential. The exponential have always mandatory horizontal asymptote at y equals 0. But remember, in the inverse function, the horizontal asymptote now is converting to vertical asymptote. So we have, in red color, let me try, one vertical asymptote here for the logarithmic vertical asymptote at x equals 0. And it's a classical. So this, so you continue down, you approach it, but never touch. It's a asymptotical approach to this. I did quickly, by hand, 3 point, 1, 2, 3, and also the vertical asymptote, que is common for the any exponential. And the logarithm, well, we need 3 points also, 1, 2, 3, but you have now horizontal asymptote. The asymptote is important piece of information in the graph. So if you are doing the graph without asymptote, this is totally incomplete. You don't receive totally credit for this graph. And number 5 is the last property, is exactly the very cost. So any logarithmic, well, no universal. It's without transformations. You have horizontal shift change. But suppose the basic function, it doesn't matter the base. We have vertical asymptote at x equals 0. Any 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 horizontal. And you see one more time. Let me try to take advantage of this moment to emphasize. Focus it, please, in the graph of the logarithm. Get the red color. You see that the domain involve only positive value. We have no logarithmic graph in the negative value. Here, no, only in the positive part. And in zero, no, because it's asymptotic and never touch. Entonces, confirmation, now graphically, to understand much better, que the domain of the logarithm is only positive. Okay, now to see more clear this idea, I propose you go to Desmos. In Desmos, I clarify everything. Let me try. Any question? Do you understand everything? Too much information? Oh no? No question, guys?
I understand.
Okay. Who are you? Claudia.
Jenny.
Jenny. And the rest, everything okay? I want to see Camila, Rachel, Andrés. Okay. Oh, everybody is okay. Okay. So let's go to Desmos to show you the elegant graph. No, roughly by hand. Look at that. Again, let me try to share the screen of the Desmos. There you go. Desmos. Do you see Desmos now or no?
Yes.
Yes. Okay, let me try. Let me see this. Oh, yes. Look at that. First of all, I want to show you one more time the graph of the exponential. Okay, you are familiar very well. You remember very well the exponential. In this case, the exponential is base 2 because it's easy to do that. Remember, 3 points is enough. Universal, 0,1, 1,2, que es 1, a, que es the base, and 1, reciprocal of the base, que es 1 over 2, que es 1 half, que es 0.5. And don't forget the horizontals. Okay, clear. Now let's move on to the logarithmic of the same base. Wow, look at that. Okay, let me review again. Logarithm of 1 is 0. Logarithm of 2, base 2, of course, we are talking about base 2. Look at the base. Is 1. Logarithm of 4 is 2, and so on. And logarithm in between 0 and 1, que I suppose que in this interval you obtain negative value of the logarithm 0.5, que is 1 half, and negative 1, 0.25, que is 1 over 4, 1 quarter, negative 2, and so on. 1 over 8, 1 over 16. And you see perfectly que symmetric with respect the line y equal x can represent the identity function. One more time, confirmation. They are inverse function each other. Entonces, what happens, guys, if you combine exponential and logarithm together in one composite function? What do you think it happened? No idea? Composition? We are doing in the example of the inverse function, you in order to verify our, okay, let's do it after. Let me finish the idea for the graph. Suppose now, okay, suppose now okay, we have this exponential, get 1 half, get decay. Okay, you know very well okay, this is symmetric with this. This is two family, two exponential. The blue one is base 2 and the red one is base 1/2. So 2 to the negative 1 power. However, I want to discuss in the logarithmic. Suppose now in the example for logarithmic base 0.5, sorry, 0.5. Okay, and decimal, I confuse it, is 0.5 and decimal is not possible to put the fraction in the base. But 0.5 is okay. So now the graph look like that. Boom. Let me show you. Boom. Again, the same idea, but now we are talking about the exponential decay. Exponential decay, and we have the new logarithm is decreasing. The new logarithm is the purple color graph is the graph of the logarithm base 1/2. Let me try to understand a little bit. Let me try. For example, logarithm 1 again is 0. Logarithm of 2 is -1. Logarithm of 4 is -2. So it's completely backward. The logarithm of the number greater than 1 is negative, and logarithm in between 0 and 1 are positive. So logarithm base 1/2 of the 1/2 is obvious que 1. Entonces le ponen 0.5,1 and 0.25,2 and 1/8,3. Do you follow me? Do you follow me? Clear or confusing? Okay. Let me try come back to the whiteboard and explain the complementary property to be ready to start working seriously with the logarithmic application. Okay, we have different property I want to discussing. This is the complementary property for the logarithmic. We studied the basic, now complementary more complicated. Property number 1, complementary, is, you know, this logarithm of the any base. Any, I put any, like a of 1 is 0. This idea is clear, right? Yes or no? Clear or not clear? Super clear. We still, oh yeah, sorry, carajo. Switching to whiteboard. There we go. Thank you. Okay, the thing I played was, okay, we studied the complementary property for the logarithmic. The first complementary property, okay, you need to know is almost by memory. Okay, logarithm of the any base of 1 is 0. So logarithm base 5 of 1 is 0. Logarithm base 10 of 1 is 0. Logarithm base 1/2 of 1 is 0. If the number inside the argument is 1, regardless of the base, the answer is 0. That is the reason that the famous point is the point 1, 0. It's the universal point of the logarithm. This idea is clear?
Yes.
Okay. Now, likewise, property number 2 complementary is logarithm of the any base of the same number as 1. Example, to understand this. Suppose logarithm base 5 of 5 is 1. Logarithm base 10 of 10 is 1. When they are coincidence in between the number and the base and the number inside the parenthesis is 1. It's obvious, right? Logarithm of 1/2 is 1. This property number 2 is clear. This is P1, P2, property number 2. Clear? Super clear or no?
Yes.
Okay. Property number 3, a little bit confused. 3 and 4 is, is the couple of property that somehow they are similar idea. This is the composition. Remember, I suppose you remember this idea. Any function composition is inverse, give me identity. Or inverse composition f, give me identity. I suppose you remember this idea. But we are talking about specifically exponential and logarithmic. You know that they are inverse functions. Suppose in the property number 3, that the innermost function is the exponential. Thus you have, for example, logarithmic of the any base of a to the x. Okay, the thing I am doing is, you have the exponential, you have x, you have exponential first, okay, this function, and after that, you apply logarithmic function. Okay, that's the outermost function. And suddenly happen when you apply exponential and logarithm simultaneously, like a composition, like a one change, the answer is the same value because they are inverse functions. And the answer is identity. Do you understand this idea or no?
Yes.
And this is applied for any number, positive or negative. Because if you apply negative here, negative number, the exponential give me positive number, and logarithm, yes, accept positive number, and the answer is the same number. So it's like a shortcut. The person I don't like is you cancel out the logarithmic and the exponential. I don't like this. Bueno, when you are doing multiplication and division, you cancel out here. Yeah, this is classical, but here, no, no good. At least in my mind. And likewise, so you apply, for example, the exponential first, and inside the argument of the exponential, no x, no x, no x, no x anymore. It's logarithmic. Similar situation happen. But the only thing is that you apply logarithm first and the innermost, and exponential secondly. And you get again identity. What is the differences between this property and this property? The difference is in the first one, P3, accept all real number, positive or negative. In this case, no. In this case, only accept positive number because negative is completely out the domain of logarithm. So this is for greater than 0 positive, and this is no. This is positive or negative, or real number. Because the magic of the exponential convert negative exponent to positive result. Okay. Okay. Now I want to explain two more properties. Actually, it's a property, complementary property for the logarithm. We are using from today every day. Property 5, property 6, and property 7. And this is the magic of the logarithm. Property 5 allow us convert, you have logarithm of the any base of the multiplication to expression. I want to call m and m. And the magic of the logarithm convert into logarithm. You can expand logarithm of m plus logarithm of m. Keep in mind, multiplication convert to addition. And we can use this property in both directions, in this direction or in this direction. And this direction is expand. And what you have, we are using in both directions. Y en calculus, we are using in both directions. You use expand, you have a complicated expression, and you separate in elementary using logarithmic. And you apply calculus separately in one expression that is super easy. Another possibility is condensing. Condensing. You have, for example, you have 2 logarithms, 3 logarithms, 5 logarithms, 20 logarithms, and you condense it in only one. It's fantastic. It's fantastic in algebra. Okay, you solving logarithmic equation, and this logarithmic equation contain 5 logarithms, and you condense it in only one. That's super easy. And similar, we are doing in the division m divided by m is subtraction. So the expression in the top is positive, and the expression in the bottom is negative. Okay, cool. Now, logarithm of number 7 is super important. In my opinion, it's the most important property. Well, no. Number 7 and number 8. Number 7 is you have logarithm of the any base of the one expression I want to call m, and this expression is raised to the r power. R is exponent, guys. M is expression. A is the base. This is the magic happening. This R, que es exponent, go to the front as a factor. This is R times logarithm base A of M. And this is fantastic because this allows us convert logarithmic equation to linear equation or quadratic equation. So this is the traditional way without using the common base. Common base is nice, but it's weak because apply in one specific example in which you can find common base, but you cannot find common base like the classical example 2 to the x equal 3. The fantastic way for solving this equation, not today, next time I promise, case solving is using this property number 7. And property number 8, let me spend the rest of the time explaining detail property number 8. Guys, please, next week, everyone bring calculator because we need to calculate to understand this. Okay? Everyone bring calculator next time. Go to the, if you have no one, go to the Walmart or go to the, store, the Office Depot to find a calculator. Property number 8 is, well, this and this is the most important, 7 and 8. Property number 8 is important, and it's important and receive a specific name. Change of base formula. It's a formula que allows us change the base. Suppose you have, I don't know, logarithm base 3 of 81, and you can change the base to a standard base. So we have a standard base. Now when you open the calculator, any calculator have 2 standard base. Because it's impossible to cover in one device, in one electronic device, any possibility of the base, 3, 4, 5, 2.5, 1/2. No. We standardize. We have 2 possibilities. Common base and natural base. Oh, common logarithmic, sorry, is the name. Common logarithmic and natural logarithm. Logarithmic HMS. Okay, what is that? Common logarithm is using in science, physics, chemistry. Student, I need to take that using common. And the most important thing is the base is 10. It's 10. There are many formulas in science. For example, the formula for the pH in chemistry, the formula for the decibel in physics, que somehow involve logarithm base 10. And the most important thing is, if the logarithm is base 10 of the one number, the right way to write this is you put logarithm of x and you omit the 10. So when you see logarithm, wow, and no specification, the base, normally you see a small number here. When you see it's missing, it's because default is 10. Okay? 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 Okay. Okay, in our calculator, we have one key, it's just log, and in the story. Let me try again the picture for this calculator que I have here. That one. And this scenario, this key, que es log, is common. And default, I suppose que the base is 10. And the natural, well, the natural is different. The natural, the base, is the famous Euler number que es E. You know, it's approximately 2.7181 something, infinity decimal place. And the notation, so log, when you indicate base E of any number, is the notation everyone in the world knows is Lm of x. Is another key that we have here. Look at that, Lm. Okay, this is a classical. Now, what is the reason I explain this? Well, the reason I explain this is because in the property number 8, in the chain of base formula, I want to write now and explain, we can compute any logarithm. So you have no forgiveness to know the value for the any logarithm because you cannot do it by the intuitive way you can do with the calculator. So this is super important. So some example using intuition is perfect, but this is not too much. It's a few amount of the example that we can use in intuition. The rest, no, because it's irrational number. Because it's irrational, I cannot use my intuition to see irrational number. So now, for example, what is the formula? I want to explain in detail the formula, and after we apply in this example, and that's it for today. La fórmula say, logarithm of the one base of the one number que I want to call x and the base I call a, okay, is equal the division logarithm of the same number, but we use a new base I want to call b. This is the original given base, and this b is the new base. And why no? Si I using the calculator, maybe the new base is the standard base, or log or lm. And the beauty, the magic is independent of the key that you press, you get the same answer. Divided by logarithm of the b, is the same new base again, of the old or given base. This is the formula. Bam, 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 bam. Very, very important, that formula. Very, very important. And there are problems that it's impossible doing without this formula. Because it's magic. You convert one crazy logarithm. Suppose that we have one logarithmic equation that contains two different bases. And nobody can solve in that. Honestly, you will be able to convert both logarithm and only one common base, and so you solve the problem. Let's apply this. I repeat that part next Monday. Okay, so I suppose in this moment everyone bring calculator. I bring, of course, my calculator physically. I bring another calculator virtual. I want to show you and we compare the answers. Suppose that I need to compute without calculator this number. Pero we have calculator. We have calculator. We are doing by hand the answer is 4. Suppose que I put in a calculator like that. You press the key LG. Okay, default the base is 10. And you put 81, the same number. Divided by LG of 3 is the given base. And when you put in the calculator this, the answer is 4. Suppose that another student doing that way. ln 81, ln of 3. Oh, same value, guys. So I want to show you this example again in Monday and another example to manipulate the famous change of base formula. Okay? Too much for today. So guys, remember, I am your friend, not your enemy. Let's see, I see you are lazy. You are doing nothing. Give the opportunity some students. Let me start recording.